Hey everyone, welcome back to Incognito Engineer. In today's video, we are going to talk about Hadoop, what it is, why it exists, how it works internally, and where it fits in the big data world. If you're a beginner, don't worry, this explanation is designed to be simple and step by step. So let's get started. Before we talk about Hadoop, let's understand why it was needed. As applications grew, data started increasing very fast. Companies were no longer dealing with gigabytes of data, but terabytes and petabytes. This created problems that traditional systems could not handle efficiently. These problems are commonly grouped under the term big data. Big data is usually explained using these three characteristics. The first is volume. This means the amount of data became too large to store on a single machine. The second is velocity. Data started coming in continuously, sometimes in real time. The third is variety. Data was no longer just rows and columns, it included logs, text, images, videos, and more. Because of these three challenges, traditional databases became slow, expensive, and unreliable. This is the problem Hadoop was designed to solve. So, what is Hadoop? Hadoop is an open source framework used to store and process large amounts of data. The key idea behind Hadoop is distributed computing. Instead of scaling vertically by buying bigger machines, Hadoop scales horizontally by using many machines together. This approach makes the system more scalable, cost-effective, and fault-tolerant. Hadoop provides fault tolerance by replicating data across multiple machines. If one machine fails, the system continues to work. Hadoop is also highly scalable. We can add more machines to the cluster without changing the application. Another important feature is data locality. Hadoop moves computation closer to where the data is stored, instead of moving large data across the network. Now that we understand what Hadoop is, let's look at how it is structured internally. Hadoop is not a single tool. It is a collection of components, and each component is responsible for solving a specific problem. Understanding these rules will make the rest of Hadoop much easier to follow. At a high level, Hadoop needs to solve three main problems. First, it needs to store large amounts of data reliably. Second, it needs to process the data efficiently. Third, it needs to manage resources across many machines. Each Hadoop component exists to solve one of these problems. HDFS, storage problem. HDFS is responsible for data storage. It stores large files by splitting them into smaller blocks and distributing them across multiple machines. HDFS stands for Hadoop Distributed File System. So HDFS also replicates data to handle failures. So HDFS solves the problem of scalable and fault-tolerant storage. Yarn is responsible for resource management. In a Hadoop cluster, multiple jobs may run at the same time. Yarn decides how much CPU and memory each job receives. It ensures that resources are used efficiently across the cluster. MapReduce is responsible for data processing. Processing large datasets on a single machine is slow. MapReduce allows Hadoops to process data in parallel across multiple machines. This significantly improves performance for batch workloads. Hadoop Common contains shared libraries and utilities. These are used by all other Hadoop components. It provides the basic service required for Hadoop to function. Let's now understand how Hadoop stores data internally. Storing very large files on a single machine is risky. If the machine fails, the data is lost. HDFS solves this problem by distributing data across multiple machines. NameNode. The NameNode acts as the master of HDFS. It does not store actual data. Instead, it stores metadata such as files names, directory structures, and block locations. This allows Hadoop to quickly locate where data is stored in the cluster. The data nodes are responsible for storing the actual data. Files in HDFS are split into fixed-sized blocks. These blocks are stored across multiple data nodes. To handle failures, each data block is replicated on multiple data nodes. If one data node fails, the data is still available from another node. This is how HDFS achieves fault tolerance. So how Hadoop HDFS works together? When a client wants to read or write data, it first contacts the NameNode. The NameNode provides metadata information. The client then directly interacts with the data nodes to read or write data. This design keeps data transfer efficient and scalable. Storing data is only one part of the problem. The next challenge is processing large amounts of data efficiently. Processing everything on a single machine is slow. Hadoop solves this using parallel processing called MapReduce. In the map phase, the input data is divided into smaller pieces. Each piece is processed independently by different machines. This allows Hadoop to process data in parallel. After the map phase, Hadoop automatically groups intermediate results. This process is called shuffle and sort. It ensures that related data is sent to the same reducer. This step is handled by Hadoop, not by the developer. In the reduce phase, the group data is aggregated. Reducers process the data and produce the final output. This output is then written back to HDFS. Why MapReduce matters? MapReduce simplifies distributed processing. Developer focuses on business logic, while Hadoop handles coordination, failure, and parallel execution. In Hadoop version 1, job execution was managed by two components. The job tracker acted as the master. It was responsible for job scheduling, resource management, and monitoring. Task tracker. The task tracker ran on worker nodes. It executed tasks assigned by the job tracker. Each task tracker had a fixed number of slots for running tasks. This design worked when clusters were small. As clusters grew, the job tracker became a bottleneck. If the job tracker failed, all running jobs were affected. This created scalability and reliability issues. To overcome the limitation of Hadoop V1, Hadoop version 2 introduced Yarn, yet another resource negotiator. Yarn separates resource management from job execution. The resource manager manages resources across the entire cluster. It decides how much CPU and memory each application receives. The node manager runs on each worker node. It monitors resource usage and manages container on that node. For each application, Yarn creates an application master. The application master negotiates resources and coordinates task execution. A container represents allocated CPU and memory. Task runs inside containers. Containers provide resources isolation and efficient utilizations. Why Yarn is better? This architecture removes the single point of failure. It improves scalability and allows for to do multiprocessing in parallel. This makes Hadoop more flexible and powerful. HDFS handles storage, MapReduce handles processing, Yarn manages resources. Together, they allow Hadoop to process large data reliably and efficiently. Hadoop by itself provides storage and batch processing, but working directly with HDFS and MapReduce is complex and low-level. To make Hadoop easier and more practical, additional tools were built around it. This collection of tools is called Hadoop ecosystem. Each tool in the ecosystem solves a specific problem. Hive was created to make Hadoop easier for people familiar with SQL. Writing MapReduce code required programming knowledge. Hive allows users to write SQL-like queries instead. Internally, Hive converts these queries into MapReduce or Spark jobs. This makes Hadoop accessible to analysts and data engineers. Pig is another data processing tool in the Hadoop ecosystem. It uses a scripting language called Pig Latin, which is simpler than Java-based MapReduce. Pig is mainly used for ETL operations such as filtering, transforming, and aggregating large datasets. Pig reduces development time compared to writing MapReduce directly. HBase is a NoSQL database built on top of HDFS. HDFS is optimized for batch processing, not for random read and write operations. HBase solves this problem by providing real-time read and write access to large datasets. It is commonly used when low latency access is required. Spark is a fast data processing engine that can work with Hadoop. Unlike MapReduce, Spark performs processing in memory, which makes it much faster. Spark is often used for iterative algorithms, machine learning, and real-time analytics. In modern systems, Spark is frequently used instead of MapReduce. Sqoop is used to transfer data between Hadoop and relational databases. Many organizations store data in traditional databases like MySQL or Oracle. Sqoop allows data to be imported into HDFS and exported back to database efficiently. This helps integrate Hadoop with existing systems. Similarly, Flume was used to stream logs and other type of data into the HDFS. Oozie is a workload scheduling tool. In real-world applications, data processing involves multiple steps. Oozie allows these steps to be scheduled and managed as workflows. It helps automate Hadoop jobs. Together, these tools make Hadoop practical for real-world use cases. Hadoop provides the foundation, and the ecosystem tools extend its capabilities. Now let's understand how Hadoop works end-to-end using a simple flow. First, a user submits a job in the Hadoop cluster. This job can come from tools like Hive, Pig, or Spark. The job request goes to Yarn, which is responsible for managing cluster resources. The resource manager decides where the job can run. It launches an application master for that job. The application master negotiates resources with the resource manager. These resources are allocated in the form of containers. Each container has a specific amount of CPU and memory. Tasks run inside these containers on a worker node. During execution, tasks read data from HDFS. Hadoop follows the principle of data locality, meaning tasks are scheduled close to where data is stored. This reduces network overhead and improves performance. After processing is complete, the results are written back to HDFS. Once the job finishes, the application master releases the resources. This is the complete end-to-end flow of a Hadoop job. Hadoop is powerful, but it also has limitations. Hadoop is mainly designed for batch processing. This means it is not suitable for real-time or low-latency applications. Setting up and maintaining a Hadoop cluster can be complex. It requires careful configuration and monitoring. HDFS is not efficient for handling a large number of small files. Each file requires metadata in the NameNode, which can become a bottleneck. Hadoop jobs often have high latency. Even simple jobs may take time to start due to resource allocation. Because of these limitations, Hadoop is often combined with or replaced by tools like Spark. However, Hadoop is still widely used as a storage layer. Hadoop may not be perfect, but introduced the idea of distributed storage and processing at scale. Many modern big data systems are built on the concepts Hadoop introduced. To summarize, Hadoop was created to handle big data challenges. HDFS provides distributed and fault-tolerant storage. MapReduce enables parallel data processing. Yarn manages resources and job execution. Together, these components allow Hadoop to process large-scale data reliably. That's all for this video. If this explanation helped you, please like the video and subscribe to Incognito Engineer. Thank you for watching.